What's up guys, it's Simon Fiaz and today's video is on aka Chemistry A-Level Halogenoalkanes. So let's get this done. Use IUPAC names to name CFC11. It's obviously going to be trichlorofluoro methane because you only got one carbon. So trichlorofluoromethane. Your equation for this reaction, molecule of this, so we've got CCl3F breaks down to form a chlorine free radical, and therefore the other thing has got to be this as a free radical. That's it. Part C uses data to estimate the number of molecules that can be destroyed by this much of CFC11. So first thing I can see is that I can find out the moles of CFC11 very easily. Mass over mR. I want this in grams, so 500 grams divided by the mR, 137.5 given in the question. But I want to now estimate the number of molecules that can be destroyed. So first thing I'm going to have to do is times by the number of moles by Avogadro's constant, which is 6.022 times by 10 to the power 23. I'll just label it as L. But then I also need to times it by, because I know one molecule causes destruction of this much molecules of ozone. So I need to times it by 100,000. And if I do that, I get 2.19 times by 10 to the power 29. Say the benefit to life of Earth of ozone in upper atmosphere. Classic question. Absorbs harmful UV radiation. It suggests one reason why the use of CFCs was not restricted until several years after Rowland and Molina published the research. The idea that there's lack of alternatives to chlorofluorocarbons. State and explain how it is able to contribute to global warming. Okay, this one's a bit trickier compared to the rest, but I know it absorbs infrared radiation and the molecule has polar bonds. So that's really what, because 2 marks, so looking for that. Absorbs infrared radiation, molecule has polar bonds. And then okay, this one says which compound is not formed by reacting 3-bromo-3-methylhexane with warm ethanolic potassium hydroxide. 3-bromo-3-methylhexane. One, two, three, 4, 5, 6. 3-bromo-3-methylhexane with ethanolic potassium hydroxide. Now this is going to be an example of elimination reaction. Obviously we form an alkene. Now what's going to happen is that, okay, let's just go for an example. OH minus a lone pair of electrons acts as a base, takes a proton, left carbon has a spare electron, and then left carbon spare electron, so wants to form a double bond. In order to form a double bond, CBr bond must break, and so you form a double bond here. But you can also do it here. Yes, you can also do it there. So 3-methylhex 3-ene definitely can be formed. Same with 3-methylhex 2-ene, because you can do it that other way around. That way, 2-ethylpent 1-ene pentguanine. Ethyl group in a second. The answer is going to definitely be B. You can't form 3-methyl hex guanine. How can a carbon-carbon double bond be here when the CBr is here? So the answer is B. Question below refers to the reaction of 1 brom of propane with a solution of potassium cyanide, aqueous ethanol. What is the organic product of this reaction? So, halogenoalkane with potassium cyanide. Nitriles are formed by reacting halogenoalkanes with potassium cyanide. So I'm going to form a nitrile. So already I can eliminate A and B thanks to my mechanism knowledge. So it's a propane nitrile, is a butane nitrile. Well, all I'm doing is I'm swapping the bromo with the cyanide, so it's just going to be methane, ethane, propane. Instead of 1 bromo, it's just going to be cyanide. So it's just going to be propane nitrile, right? No, because I've got 1, 2, 3, 4 carbons, therefore it's going to be butane nitrile. Question 4, which row correctly shows the compound that has a faster rate of reaction? The correct reason for this. It's definitely going to be A, and all it's testing is your knowledge on the, what's it called again? It's a very short, but they always like to ask questions on it. The bond entities of CBr, CCl, Ci, and Cf, and all of that. The answer is A because the CBr bond is weaker than the CCl bond. Outline the mechanism for this reaction. So I've got CH3, CH2, oh shoot, CH2, Br, partially positive, partially negative, lone pair of electrons and C triple bond N, 9 is charged, attacks carbon, CBr bond breaks, and I form that. That's it. And then I've still got the lone pair of electrons with Br minus, and then the potassium from the potassium cyanide will bond to it, and then it will form eventually KBr because potassium positive and Br is negative. So yeah, it goes there, and that's it. I don't think it wanted this extra step, just wanted that. Give the UPAC name of D. Well, it is methane, ethane, propane. There's obviously nitrile, so it's going to be propane nitrile. Calculate percentage atomic economy for the formation of D in this reaction. Percentage atomic economy, MR of desired products all over MR of all reactants times by 100. So MR of desired products divided by MR of all reactants times by 100. So for the formation of D, that's the desired product. D, well, that's that. So the MR of that over the MR of all reactants, so all of this. So it would just be MR of propane nitrile 55 divided by total MR of, in this case, that and potassium cyanide. You should get 174 as a total MR for that, times by 100, 31.6%, 3 significant figures. Question 6. Which compound can react with ammonia to produce propylamine? Now, propylamine, halogenoalkanes can react with excess ethanolic ammonia to form amines. So it needs to be a halogenoalkane. So it's not A, that's got a carbon-carbon double bond. It's not B, that's got an OH group, that's alcohol. The answer is going to be C because of that Br. Yeah. And D, well, if you look at D, that's C3H4, 5, 6, 7, 8. So that's C3H8. That's just an alkane, not a halogenoalkane. Then it says C. Which compound could not be produced by reacting 2-bromo 3-methyl butane with sodium hydroxide? So this can either undergo nucleophilic substitution or elimination reaction, right? So which one? So in this case, we formed alkenes and we've also formed alcohols. Could not be produced methane, ethane, propane, butane, 3-bromo, 2-bromo, 3-methyl. So in the normal reaction, what would happen in nucleophilic substitution? It just replaces it. So you've got your OH group here. So it would just be 3-methyl butane 2-ol. Yeah, 3-methyl butane 2-ol. So that definitely could be produced. Or it undergoes elimination reaction where you form a double bond, OH minus acts as base, takes a hydrogen. So for example, in this case, OH minus acts as base. Let's say, well, actually, let's put the 3-methyl group here, put the hydrogen here, takes a hydrogen, here you go, CBr bond breaks, and there's a double bond. So it can be 1,2-methyl butene, no, sorry, yeah, 2-methyl butene that could be produced, 3-methyl butanone, yeah, because if you do it from this direction, so you got a hydrogen here, OH minus here, takes a hydrogen, there you go, CBr bond breaks, and now you form the carbon-carbon double bond on the first carbon, so it will be 3-methyl 1,2,3 butanone, and that will be produced. 2-methyl butanone, so the methyl groups on the second carbon, no, that is not the correct answer. That cannot be produced. Compound A is a halogenoalkane named compound A. So we've got 3-chloro dash 2,4 dash di methyl. What's the longest carbon chain? Methane, ethane, propane, butane, pentane. So 3-chloro dash 2,4 dash dimethyl pentane. Drawn figure 1, the peaks in the main spectrum. So I know chlorine consists of two isotopes, 35Cl and 37Cl, 75% is 35Cl. So what I want is one at 134 at 3, I guess squares high, rectangles high, and then one at 136, just like that. Yeah, it should be a bit lower than that. Question C, outline the name of the mechanism for this reaction. Warm dilute aqueous sodium hydroxide, so it's going to be elimination and not nucleophilic substitution. And then outline the mechanism. So what will happen is takes the hydrogen, CBr bond breaks, left carbon spare electrons, so wants to form a double bond, Cl bond breaks, and then all that happens is you've got everything else should stay the same except for that you've lost the Cl now. It leaves with lone pair of electrons. You still got this hydrogen. You got the CH3. You've got your hydrogen here. You've got your hydrogen here. You've got your hydrogen here, and you've also formed H2O. That's it. Oh, it's warm dilute aqueous sodium hydroxide. It's not. I thought it went warm dilute ethanolic because it's aqueous. This is just completely wrong. It'd be nucleophilic substitution. And if this was a real exam question, well, it is a real past paper question, I'm pretty sure, I would have lost 4 marks. So that's not great. Need to get rid of this. So nucleophilic substitution already NS. And what happens is, in this case now, well, it's just going to replace, so it's going to attack the partial positive carbon and see Cl bond breaks. That's all that happens. and then you form your CH3. Obviously you should draw it out fully, but I just don't want to waste any time. Carbon, and here you've got your OH, so your OH, hydrogen, CH3, H, C, H, 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 and again the Cl minus leaves with a lone pair of electrons. Cl leaves a negative charge lone pair of electrons. In this case, because it's hot ethanol potassium hydroxide, it is elimination. And I know it's elimination because you form an alkene. And the role of hydroxide ions in elimination is acts as a base, aka takes a proton acceptor, and in this case it takes hydrogen, left carbon spare electron, CCl bond breaks. And what I was meant to do for part B, I did for part D, I did for part C, which is fine. You got your form carbon carbon double bond, Cl leaves, and that's it. Plus H2O plus your Cl minus with one pair of electrons. Elimination acts as a base, takes it there, that leaves, and you form that. Perfect. Acts as a base proton acceptor, whatever we want to say. And yeah, that is worth 6 marks for that and 4 marks for part C. So that just shows you need to know your mechanisms in detail. Obviously these are pretty nice mechanisms. Well, the ones you first learn, nucleophilic substitution, and then later on you learn about elimination. Tick the box that shows the correct compound. Alcohol B, alkene C. So what you'd have to do here in this case, you just look at the peaks, right? Obviously we don't really care about region below 1500 centimeters to power minus 1, that's fingerprint region. And if you look at the peaks, well, we can see a carbon as this, so we've got a carbon-carbon double bond, 1620 to 1680 centimeters to power minus 1. Therefore, it's going to be the alkene C. Compound D reacts with dilute aqueous sodium hydroxide, similar way to A to form alcohol B. Explain why D reacts more quickly. This one you need to spot this. CCl, CBr, and the same thing, bond enthalpies. So, CBr is weaker than CCl. Actually, this topic is very common. Is weaker than CCl. Actually, it's only 1 mark. So yeah, I was about to waffle on. CBr is weaker than CCl. CBr is lower bond enthalpy, breaks more easily, but it's 1 mark. So CBr is weaker than CCl, or I just say CBr has lower bond enthalpy than CCl. Which species could act as a nucleophile? BH3, boson group 3 bonded to 3, so no. NH4 plus, no. pH3, phosphorus group 4 bonded to 3, yes, could act as a nucleophile. Nucleophile electron pair donor, and will have electron pair. SiH4, no. And it says, how many more questions left? Okay, still quite a bit. It says 2-methyl propane 1-ol, so an alcohol, can be prepared by reacting propane with dilute aqueous sodium hydroxide. So it's going to be nucleophilic substitution. Don't fall for the mistake I just made previously, like just thinking it's elimination immediately. It was nucleophilic substitution. Nucleophilic substitution. So all I have to do here is 1 bromo 2 methyl propane, methane ethane propane, 1 bromo 2 methyl, fill in the hydrogens for 3 marks. Okay. Sodium hydroxide, lone pair of electrons and OH minus. And all it's going to do, well, that's partially positive, partially negative. I don't think AQA even cares if you include them or not. Partially positive charge, attacks partially positive carbon, CBr bond breaks, and all you form now is this. You replace the Br with the OH functional group, and you're left with 2 methyl. Oh yeah, that's a methyl group. Oh bad. 2 methyl propan 1-ol. Part B says, okay. Okay, this is gonna look tricky. It says when 2 centimeters cubed of that was reacted with excess sodium hydroxide, this much of methyl propan 1-ol is that. Calculate percentage yield for this reaction. The density of 1 bromo 2 methyl propane is that. I know the volume, I know the density, so I can find out the mass, I can find out the moles. There's a 1-to-1 molar ratio, so therefore I can find out the mass of that, and then I can do 895 milligrams and you convert it to grams. I think I forgot how to do that, so I'm gonna have to search that up. I think it's divided by 1000 anyway, and then just do that divided by theoretical yield. Okay, so actually it's not, it doesn't, it's just a lot of steps. So first thing I need to use is density is mass over volume. Therefore, mass equals density times by volume 2 centimeters cubed times by 1.26. Okay, let's put that in the calculator. 2.52. Now I can find out the moles of, obviously in the exam I'd write down what I'm finding out the moles of, in this case of 1 bromo 2 methyl propane, so just draw a curly arrow there, which is just going to be the mass, which I just worked out, divided by the MR, which is given in the question there. Then I know it's a 1-to-1 molar ratio, so that is also equal to the moles of alcohol, the alcohol, and so now I know that, well, moles and mass of MR mass is going to be the moles, so this times by the MR of 2 methyl propan 1-ol, 74, and this will give me the theoretical yield. And so then we're almost there. I get 1.36. Obviously that's in grams, so I need to convert this into grams. I'm pretty sure I divided by 1000, so 0.895 divided by my answer times by 100. 65.7%. Perfect. 65.7%. Milligrams to grams. We divide by 1000, aka times by 10 to the power minus 3. The percentage yield formula I forgot to mention, if you guys didn't know, is actual yield. So what we actually make over theoretical yield. Theoretically, what we could make. Theoretical yield, and because it's a percentage, we also times by 100. Okay, part C says when 1 bromo 2 methyl propane reacts with hot concentrated ethanoic potassium hydroxide. So the name of the mechanism in this case is going to be elimination, as I use ethanolic potassium hydroxide. Name the organic product. Okay, naming the product is going to be a bit more of a bit harder than the other part. So I'm just going to probably just go through the mechanism. Yeah, because that was with nucleophilic substitution. So yeah, I might just do that. Methane, ethane, propane, 1 bromo, 2 methyl. Fill in the hydrogens. Obviously, fill in the hydrogens. and in this case the OH minus ion acts as a base, takes a proton. So it's going to take a proton, left carbon as a spare electron, wants to form a double bond, order to form a double bond, CBr bond must break. And so now what I form is my CH3, my CCH3, double bond here, C, H, H. That's it, right? CH. One pair of electrons leave, and I also form H2O because it's bonded to this hydrogen to form H2O, water. Yeah, so what is that? It's definitely going methane, ethane, propane, but propene. So it's just going to be methylpropene. Or 2-methylpropene. And obviously the elimination. Question 11, which compound has fastest reaction potassium cyanide to form pentane nitrile? So one bromobutane, I've got the CBr, I've got the CCl for part B, I've got the CF, and I've got the CI. What I should know is that CF is the strongest one, so that's going to have the slowest rate of reaction. And I should also know that CI, CF, CI is the weakest one. So therefore, 1-iodobutane will have the fastest reaction. Question 12, which of the following mechanism does not occur in reactions of bromoethane? So what is bromoethane? It is a halogenoalkane. Now elimination definitely does occur in reactions of halogenoalkanes. Same with nucleophilic substitution, so I'm left with A and D. Electrophilic addition, no, that is with alkenes. I guess you could become mixed up with radical substitution, but remember you could also form halogenoalkanes. You could also have a reaction with bromoethane in free radical substitution, but with electrophilic addition, no, because it's about the carbon-carbon double bond. Question 13, which of the arrows labeled A, B, C, or D in the mechanism and diagram is not correct? First one, yeah, B, that is correct, CBr bond breaks. Then you've got this, D, yeah, C definitely is not correct. 13C. Question 14, which of the curly arrows and mechanism is not correct? One, that is correct, CBr bond breaks, yes. Third one, yes, takes proton to form the NH4 plus ammonium ion. You can see that there, NH4Br, they'll bond to the Br with the lone pair of electron minus charge. Yeah, and what should happen is it should go there, shouldn't it? So the answer is 4. That one's wrong. Question 15, which statement about the reaction is not correct? Ethylamine is a primary amine. The mechanism is a nucleophilic substitution. It definitely is a nucleophilic substitution. Ammonium bromide is an ionic compound. Yes, you've got your NH4 plus Br minus. Is definitely ionic compound electrostatic ionic bonding and all of that. The answer is going to be C, because ethylamine definitely is a primary amine. So the answer is C. That will, using extra bromoethane will prevent further reaction to form a mixture of amine products. That is not correct. Question 16, why are fluoroalkanes unreactive? A couple of questions ago, that was here, I was talking about the CF bond being the strongest, and that's why it has slowest reaction. It's because the CF bond is very, very strong. That's why they are very, very unreactive. And that is the end of the AQA A-level chemistry halogenoalkanes question paper, physics and math tutor.